Homework 8 pertains to the Z transform. Is that correct?
Right.
Okay. So what's the question in regards to that problem? It's a partial fraction expansion problem.
Right. I wanted to ask, because for that one's an improper fraction. I want to ask how you got, how you simplified that.
It's an improper fraction. Yes. So, okay. Now, if you notice, after converting it to the positive form and taking 1 over z, it's not an improper fraction per se. Is that right? You end up with let me share my screen and showcase my solution. And I'll bring the solution so we can discuss. So if you remember, if this is the problem, is that right? Now, when we divided the x of z over z, because that's what we need to do. If you look at the order of the denominator is 4, the order of the numerator it's 3. So in this case, that's not an issue. And if you notice, you have a component that is a constant with an impulse that would appear in the inverse just due to the fact that these two had this kind of where was it? Please see. So because there's a constant here that is associated with z minus 0, which is basically just 1 over z. And when you find the inverse of that, that's what you end up getting, the delta function of n. But that's because for the x of z, we converted to the positive form. And whenever we did that, we looked at the x of z over z. So you have 1, 2, 3, and 4 versus 3 at the numerator in that case.
I was going to ask, could you go over that conversion to the positive form? Like what? Right. Go over the conversion to the positive form.
What do you mean?
Yeah, for number C, how you got from C squared minus 5z to z minus 0.25 plus the square root of 1.25 divided by 2?
How?
Yeah.
I mean, that's factorization of a quadratic equation. So if let me fix it. Just give me a second. My tablet is acting up. Just a second. Mapping on it. Okay. Now I can fix this. So technically what you did is you did, it was z squared minus 0.5z minus 0.25. Your A is 1, your B is minus 0.5, your C is this. So you did minus B plus minus the square root of B squared minus A 4AC over 2A. And then what you did is B was minus 0.5, you have a 0.5 plus minus minus 0.5 squared minus 4, A was 1, and C was minus 0.25 over 2, A is 1. So you do that, you end up with, oops, 0.5 plus minus square root of 0.25, and then you end up with minus plus 1 over 2, and this ends up being 0.25 plus minus the square root of 1.25 over 2, and if you divide this, you get 0.25 plus minus the square root of 1.25 over 2. I kept it as is because I didn't have a calculator calculating it, but you could have some, plug it into the calculator and find out what this value represents. Does that answer your question?
Yes.
Okay.
Just to be clear, we can leave our answer like that.
I mean, you have a calculator, and I mean, plugging into this calculator is just easy. Now, if you notice at the end, I did plug in these values and I represented them in the decimal values at the end. But at the beginning, for the sake of simplifying the math that I was working with, so I would get accurate results, I kept them as is. Usually, I don't give you values that would have decimals that would make your life harder on an exam. So this should not be a problem.
All right, thank you.
Absolutely. What else?
Can you do like an example of converting z from its negative to positive form?
Yeah. Let's do that. I'll do a hypothetical example. Let's say you have an x of z which equals to z, no, let's do this, 1 or 2 minus 3 z minus 1 minus 5 z minus 2 divided by 3 minus 4 z minus 1 minus 3z minus 2 plus, wow, let's do plus just because we can, 6z minus 3. That's an example where we do have a rational fraction that is given in the negative form. Now, what is the highest order between the numerator and the denominator in this case? I have z raised to power minus 3. To convert this to positive, I need to multiply with z raised to power 3. Is that right?
Yes.
And if I multiply the denominator, I will also need to multiply the numerator with z raised to power 3. Now, for the sake, if I look at the numerator has an order 2. So I technically need z raised to power 2, but to make this still z raised to power, I'll split this into something that looks like this. Now let's multiply. If I take this and multiply it with 3, x of z equals to 3z cubed plus 4z squared minus 3z plus 6. All what I did is multiply this with that, this with that, this with that, and this with that. And that's what I end up getting. Now I'm gonna keep this z here, this extra z that I said I don't need. And then I'm going to multiply this with each one of these values. And what do I get? I get 2z squared minus 3z minus 5. And that's how you convert a negative form to a positive form. Let me make it look nicer. Now, if I was asked to, do partial fraction, I can take this z and have x of z over z equal to 2z squared minus 3z minus 5 over 3z cubed plus 4z squared minus 3z plus 6, and continue with my work. Does that help, Skylar?
Yes, thank you.
Perfect. What else, guys? Any questions in regards to DTFT, Z transform, how we apply?
Yes. Could you go over 4A, homework 7?
Homework 7, what you mentioned?
4 part A. No, question number 4.
Or A, okay. So in this problem, I think this is, I had a typo in this solution. I remember I solved this, but I never fixed it. So, but I'll tell you the idea behind it. I think there's no pi or something that is not correct in it, but that's the extent of, I don't remember where I did that, but I remember I have that done. But the whole idea is that if you have a function that looks like this here, and you're asked to use the inverse ID definition or the properties of DTFT to compute the inverse of the frequency function shown in the figures below. So if I look at a function like this, for this looks like a triangular shaped function. I know from being able or have done convolution that I can get a triangular shaped function if I take the convolution of 2 pulses. So what I did here, I used the convolution property in the frequency domain. If I take the convolution of a pulse in the frequency domain with another pulse in the frequency domain, this too should generate a triangular shaped function. And that's the argument that I put forward in here. And then I said, if this is V, and this is what I can see from here, this is a function centered at 0 in here, then I can say that this value here for the pulse can be represented with its inverse, which I have from the table. It's a sinc function. And this is another function that has a sinc function as an inverse. What's convolved in the frequency domain becomes a simple multiplication in the time domain, which means that these two will multiply together if I find the inverse of each one. And then I end up with the sinc square function representing the inverse of this function. So that's the whole idea, is that for you to be able to come back and say, you know, I want to creatively figure out how I can leverage the properties to solve a problem. Other approach would have been you figuring out what this function is and this function is and use the definition, which is not going to take you anywhere to get the inverse because it's going to be complicated. Now, eventually, after 2 pages, which if you remember, this was one of the questions I asked in homework, in exam 2 when you did the Fourier transform to find the inverse Fourier transform of a triangular shaped function. You could have used the properties and got the sinc squared and case closed, but if you apply the definition, you'll get to it eventually, but it's going to be 2 pages worth of solution. So but in this case, I used the property and I used the convolution property in the frequency domain between 2 pulses. And then I used one of the tables that I have for, and I will open up this table, the DTFT table here. If you look here, I used, where is the pulse? Yep, this is the pulse here. This is the pulse function. It's defined as a piecewise, in this case, the value of 1 between n and minus n. And this gives you a function that looks like this. Or if you look at it in the frequency domain, this is equivalent to that in the frequency domain, which in a sense is what you need to apply to inverse what these values represent in this case. So that's basically it. I think this is the pulse in the frequency domain, gives you a sinc in the time domain. And since you have 2 sinc functions multiplied together, you end up with the sinc square. I think I have a typo in some of these values, or in here, I forgot which one it is. I needed to fix that and I forgot to fix it, but that's it. Does that answer your question?
Yes.
Good. Any other questions, concerns? You will be given the tables, and you will be given the formula sheet to use in the exam, so you don't have to worry about printing them out. They will be provided. Questions? Anything that is not clear in regards to DTFT, Z-transform? It's your time to ask, guys. Is it clear, the relationship between the DTFT and the Z-transform and how they're different or similar?
There's a question in the chat.
In problem 1, what does the Q means in the problem? Problem 1. Let's see what problem 1 means. Q in here. It's the center of the pulse. So if you look at this here, notice that this is centered at 2 in this case. So there is a shift in the pulse here. So the definition of a pulse is usually a a function that is centered at 0. Is that right? Now, the fact that this is shifted in time, you can see it's represented with a shift in here. And the fact that there is another pulse here in the opposite polarity or opposite sign, you'll notice that this will be centered at 6 in this case. Now, so this is equal to 2n all the way with a shift equal to 2 and a width equal to 4. So that's what this means. And then you have another pulse with a width of 2, and that pulse is centered at -6. So this is from the DTFT table. If you go back to the DTFT table here, this is what this table is. This is the n here that I had. So you can see the sign. This is omega n plus half, n being the maximum or half the width in a sense, because n is going to be positive and negative values for n. So this is going to be, let's say, centered at 0 and goes to -2 and 2. So in this case, this Q would be the width of the pulse, either 4 or 2 in this case, or half of it in that sense, because 4 is the total width here, and this goes to 2 and -2 if it was centered at 0. So you'll notice that this is 2, and this pulse goes, if it was centered at 0, this goes to 1 and -1. So n is 1. So you'll notice that Q is equal to 1. So this Q is the same as n in the pair that you have here, where n is the upper limit or the lower limit absolute in this case. I should have kept it as n, but the notion that I used here is the same notion I talked about earlier in lecture 2 or 3 when we introduced the pulse, that this is the complete width, but this n is half of the width here. So I hope that answers your question. Does that, Josh? Yeah. Any other questions? Is it clear how you do the DTFT? Yes.
Yes. For homework 8, can you just go over part A? How do you plot the poles and zeros for that transform?
Which part?
4A.
4A. 4A. How did I plot these?
Yes.
If you look at this here, what is the value of Z? The numerator is the zeros, the denominator is the poles. So if you look at the zeros here, I have a 0 at 0.5. So I went here, 0.5. This is 0.5. I put a circle. That's the 0. I have a pole at minus 7.5, which makes the denominator 0. We call it a pole. And I put at minus 0.75 an X. And this circle here is the unit circle. This is the real, and this is the imaginary axis. Since both are real, they all existed on this axis. None existed at this axis. The same thing with the rest. You look at this one. I have a 0 at 0.5, and I have a pole at 0.75. So you can see the 0 and pole are very closely located. Does that help?
Yes.
Yep. Good. Any other questions in regards to what you need to do. Anything that you are still struggling with that needs further clarification? Anything not clear, not easy to understand? Everything is good? I mean, it's very straightforward when it comes to content. DTFT inverse DTFT, Z inverse Z. The inverse involves you being able to evaluate the partial fraction expansion for rational fractions. And that's basically it. You might be given a difference equations, something similar to your quiz, and asked to find either the frequency response or the frequency or the system function. That's basically converting the difference equation that you have to either the DTFT or the Z domain and finding the H of Z or the H of omega. Either or, based on what's asked. If you're asked for frequency response or if you're asked for system function, that's basically how you will be addressing these kind of problems, which we've done examples on. If you've given rational fractions, you have to find the inverse. You use the partial fraction expansion, and there's 3 different cases for that, either real and unique roots for the polynomial at the denominator, which are the poles of this function, or you have repeated, or if you have complex. So that's basically the process that we have to usually go with. Any questions in regards to anything that we discussed thus far? Is it clear? So basically we're leveraging these domains to simplify the analysis of systems. That's what we have talked about. Either we use the Z domain or the DTFT for a discrete time. So basically all our work is in discrete time signals and systems, which means if you have a system, the system has an H of omega or H of Z, or can be represented with an H of N as an impulse response. You have an input to the system X of N, and you have an output Y of N. The output of the Y of N is basically the convolution of the 2 input and impulse response of that system. Or if you do it in the frequency domain, which is the gist of what we have done, the output Y of Z is equal to the H of Z multiplied with the X of Z, which we also said the H of Z is equal to the Y of Z divided by the X of Z, and we call that the transfer function. And that's basically it. So analyzing systems using this these domains allows us to simplify the process rather than using convolution. We end up using simple multiplication. If you're given a system with an input and an impulse response, you can find the output using simply the Z domain or the DTFT. In the DTFT, this is exactly similar. Y of omega is H of omega, X of omega, or H of omega is basically equal to Y of omega over the X of omega, as we explained in the class. So it's not any different, it's just application of that, being able to understand this and leverage that to help do the analysis of systems is basically why we have went through the whole process of explaining all these different transforms. And that's technically it, you know. For tomorrow, you're gonna have questions asking you to do DTFT, inverse DTFT, Z domain, and inverse Z transforms. So that's almost guaranteed. So should be straightforward though. Any questions, last questions before we conclude? If there's no questions, I'll let you go back to studying. I don't want to waste your time. I hear none, so good luck, guys, and I'll see you tomorrow. Study well, be prepared. Hopefully everything goes well in that sense. Have a good one.